веб-камера, она тоже хорошо пишет звук. И он уже идет.
May I continue?
Да.
Thanks a lot. During today's talk, we will, if I have chance, we'll discuss briefly water-web model. I will give you some very brief introduction, just in case somebody is not familiar with it. Then we'll discuss latent variable modeling, then the way how it can be applied to skip-gram, and in particular adaptive skip-gram algorithm. Then we'll talk about stochastic optimization that allows us to make this latent variable model practical. And finally, discuss how this diagram can be generalized in the case of big data sets. So, water-web model was suggested 3 years ago by Thomas Vetrov, who is also a speaker on this hackathon, but I discussed with him, so he will talk about different things. So actually, Mikov tried to solve quite standard problem of word prediction, and he built a special model which was which could be trained on large data sets, in particular on the whole English Wikipedia. And the essence of his model was the conversion of each word in our dictionary to vector, to point on a vector space. And the model worked as follows. So we start from the sequence of words, and the problem is followed. We take current word and we would like to predict its neighboring words. C words before the current word and C words after the current word. So this problem can be formulated as kind of machine learning problem with inputs and outputs. So these are our inputs and these are our outputs to be predicted. So we replicate each word 2C times and assign different predictions here. And this is the probability of neighbor. It can be also regarded as some score function. So the idea is pretty simple. In the numerator, there's just exponent of scalar product of two vectors. One vector is called inner representation of the word, while another vector is called outer representation of the word. So we take just scalar product and we renormalize it in order to ensure that the left-hand expression is really a probability distribution. So this function defines our likelihood, which we could maximize with respect to our training sample. On our training sample with respect to inner and outer representation. So the idea is pretty simple. What's the problem? Why this framework doesn't work? No, it should work in theory, but in practice it does not, because of high computational complexity. Pay attention that here we have normalization constant, which involves summation of all possible y primes. So the number of items here equals to the size of our dictionary. So it's usually about several tens, thousands of words, or something, or maybe 100 words, 100,000 words. So this is not practical because we need to sum it over to reach instance on our training sample. So what Mikov did, he converted the problem to so-called hierarchical softmax, where instead of predicting each particular y, we come to a so-called Huffman tree. So for our dictionary, we built a Huffman tree, where each leaf corresponds to our words in our dictionary, and for each word we have a path in this binary Huffman tree. And now the score function looks like this. So this is a product taken with respect to the nodes in our path of sigmoid or logistic functions, which look like this. And in this logistic function, we again have a scalar product between inner representation of word x. So this is the word which we're given, with which we are trying to predict something. And outer representations, not of the words in our dictionary, but outer representation of the nodes in our Huffman tree. So we can see easily that this quantity is already normalized. So if we sum it over all possible words in our dictionary, all possible y's, we'll get exactly 1. So thus we have no need in extra normalization. And that is why the complexity reduces from O of V to O of log of V.
So this is much more computationally efficient scheme. And due to this scheme, the framework itself is very efficient. In particular, it takes less than an hour to make a full pass through English Wikipedia. So this is almost fantastic. But what was even more interesting is quite unexpected properties. Well, Thomas says that he had really expected that properties. I'm not sure. Anyway, but for other researchers, it was a bit unexpected. It appeared that these vector representations, so now remember that for words we only have inner representation, so ins. So these inner representations possess some, captured some semantic properties of the words. And this is a quite famous example, and there are also thousands of them. That if we take inner representation for the word Paris, we subtract representation for the word France, we add representation for the word Russia, and we get something pretty close to inner representation of the word Moscow. And there are thousands and thousands of similar examples. So this is one more example. So it appeared that these vector representations actually learned the quite abstract concepts of gender, of number, of geography, and or some other things. So this is very nice. It seems that a computer shows the first signs of understanding the sense of data, the sense of the particular words. And now the question is, can it be used for Q&A modeling? Actually, it cannot. Why not? Because of word ambiguity. Let us consider a quite simple example, which will be throughout the whole presentation. When was the Battle of Waterloo? So if we want to answer this question, actually, what we would like to have, something like this. Inner representation for the word Waterloo, from which we could subtract inner representation of word battle, add representation for the word date, and obtain something pretty close to 1815. The problem is that Waterloo, the word Waterloo, has several meanings. And it's not clear whether computer will learn the concept of a battle, because Waterloo is also a famous railway station in London. Waterloo is Abba hit, and there are also some more meaning. Yep.
Why we should subtract battle? Why we should not just add the date?
No, that's up to you. You could play with it as well. The problem is, this was well just quite abstract example. What came to my mind, that I would subtract battle and add date, but maybe you would do something else. The problem is that if Waterloo corresponds to the station in London, we will not obtain date anyway. I mean the right date of a battle. So it's not clear whether the computer will learn vector representation which will correspond to station in London, or battle during Napoleonic Wars, or to hits of ABBA. And what we would like to have actually, we would like to learn several representations which correspond not to words but to their meanings. Taking into account that the number of meanings for each word is usually quite limited, this should not be a problem. So now summary of word2vec. So its advantages is extreme computational efficiency. So we can learn word2vec model and its various extensions very fast. Thus, we are able to process huge data sets. And actually, in the case of texts, we do really have huge data sets. So this is important to be able to train on them. Also, we know that word2vec manages to learn some abstract concepts, and so has some. It captures some semantics of the words. And what is good is that this is highly extensible concept, and it can be extended from the words to, say, images, to sentences, to abstracts. So now it is known several models like image2vec or sentence2vec, abstract2vec, and whatever. So the idea of converting something to vector appeared to be quite fruitful. What are main disadvantages? Well, probably the most important is that standard word2vec model is not able to learn vector representation for the meanings of words. And one more thing is that it is highly dependent on the choice of this binary tree. But well, Mikolov managed to suggested to use Huffman tree, and probably that's more or less okay. Now let us switch to the second topic of my presentation, latent variable modeling. So just one question: how many of you took part in previous hackathon? Please raise your hands. Not too many. Okay, good. So consider very simple example. We are given a set from a Gaussian, and we would like to estimate its parameters. So that's quite trivial, quite classical problem that every second grade student should be able to solve at least. And we know that it can be solved using standard maximum likelihood equations that allow us to obtain explicit formulas for mean and for variance. Now consider a bit more difficult problem. We are given sets of objects which were generated from different Gaussians, but we know which object was generated from which Gaussian. And the problem is, again, how to estimate the parameters of a Gaussian. So actually, it's not more difficult at all. It's equivalent to the previous problem, because to estimate the parameters of a red Gaussian, we just take red objects and perform maximum likelihood equations. When we would like to estimate the parameters of a green Gaussian, we take green objects, and for the blue one, we take blue objects. And the maximum likelihood equations are the same. So the problem starts when we do not know which object was generated from which Gaussian. So all objects are gray. And we know that they were generated from several Gaussians, and we would like to know the parameters of those Gaussians. Of course, we can always assume that there was just one single Gaussian, and then the problem is equivalent to the first case. We could perform maximum likelihood equations. The disadvantage is that this model is not flexible, and in this example, it clearly does not reflect the details in our sample. So we need more flexible model, and a more flexible model could be a mixture of Gaussians. So the question is how to estimate the parameters of those Gaussians. So, this is quite standard problem, and it is usually shown to motivate the application of EM algorithm, which we will now describe. So the way out in this situation is the introduction of additional latent variables. So if we introduce variable z, for each object we introduce variable zi, which encodes the index of a corresponding Gaussian from which ith object was generated. Then we can establish such probabilistic model. The joint distribution of x and z is given as a product with respect to all objects. Now, according to product rule, joint distribution can always be decomposed as a product of a one-dimensional conditional distribution times prior. So this is it. So what is the first term here? This is a probability of xi if we know the parameters of all our Gaussians, and if we know the particular Gaussian from which ith object was generated. So then it's quite trivial. This is just a Gaussian with the parameters mu and sigma taken from the corresponding component, from the corresponding Gaussian. And here's just prior distribution, the weight of corresponding component, which we encode with a vector pi. So we take just pi of the I. So the set of our parameters is now consists of mu, sigmas, and pi's, and mu j, sigma j, pi j, where j runs from 1 to k, and k is a number of Gaussians in our model. So if we know both x and z, the problem of maximum likelihood estimation is again pretty easy, since it's equivalent to this case. So what should we do if we do not know z? So this is a classical example of latent variable modeling. We do not know z, but we assume that there exists some z using which we can construct better probabilistic model. So now the question how to optimize so-called incomplete likelihood, or log of, or equivalently log of incomplete likelihood. This is it, log of p of x given theta. So now let us try to write down several identities. So first of all, we take this logarithm of incomplete likelihood. Why I call incomplete? Because we do not know z. If we knew z, that would be complete likelihood. And if we do not know, z. This is incomplete likelihood. So this is just terminology. So we take the log of incomplete likelihood and multiply it by 1. And here how we encoded 1. So we took arbitrary distribution with respect to z, and we performed integration with respect to z. So since log of p of x given theta does not depend on z, we can just put it out of the integral, and then the integral vanishes. So it gives 1. Now a bit more complicated thing. We write down p of x given theta as follows: as a division of a joint distribution of x and z given theta divided by p of z given x theta. Does everybody understand why this quantity is exactly p of x given theta? I would not say that according to bias theory. Actually, bias has nothing to do with it. The answer is more simple. So this is just according to the properties of a conditional distribution. So as we know, conditional distribution can always be, yes, or equivalently chain rule, can always be written as this, right? So now, and from this, it immediately follows that marginal distribution on y can always be expressed like joint distribution divided by marginal by conditional distribution. So this is it, and this is exactly what we did here. So what do we do next? We multiply the expression inside of logarithm by 1. So we multiply and divide it by q of z. Again, this is identity. And what do we do next? Well, we will split the logarithm into 2 parts. In one part, we'll combine joint distribution divided by q, and in another part, we'll combine q divided by p of z given x theta. So now we've obtained 2 terms. Note that the sum of these terms equals exactly the logarithm of incomplete likelihood. What can we say about either of these terms? Well, let us first examine the second term. Actually, it is well-known Kalber-Kleibler divergence or Keil divergence that can be thought of as some pseudo distance between a distribution. So actually it's not a distance, but it is some non-negative value that equals to 0 if and only if these 2 distributions are the same. Otherwise, it's always non-negative. Well, otherwise it's always positive. And since this is a positive value, then the first term is just lower bound for our log of incomplete likelihood. Why I call it variational lower bound? Actually, because it depends on additional parameters. In our case, it depends on q of z. And for any choice of q of z, this is always a lower bound for our logarithm of incomplete likelihood. So we can try, for example, to maximize this lower bound with respect to q of z, hoping that the larger is our lower bound, the more accurate is our approximation for incomplete log likelihood. So this is what we did. We have 2 terms. The first term is L of q theta, variational lower bound. Note that it depends on additional parameters q of z, while the left-hand expression does not depend on q of z at all. And the second term is just some non-negative value. So this is why L is always lower bound. So what is the idea of a well-known and extremely popular EM algorithm? Instead of trying to optimize this incomplete log likelihood, we will optimize variational lower bound with respect to both q and theta. And we'll perform some kind of block coordinate ascent. So we'll try to optimize it with respect to q given theta fixed, and then we'll optimize it with respect to theta given q fixed, and so on. So we'll iterate until convergence. In many cases, it appears that this block coordinate optimization can be done much more efficient than the direct optimization of this logarithm of incomplete log likelihood. So now let us see how it works. We start from this variational lower bound. So this is just a definition. I rewrote it again. And we would like to maximize it both with respect to Q of z and with respect to theta. What do? First, we fix some initial approximation, theta 0, some arbitrary value of theta. Then we perform each step. On each step, we try to maximize our variation of our bound with respect to Q, given theta fixed. So here, theta is fixed to theta 0, and we try to find maximum with respect to Q. From the first side, it seems that this is extremely complicated problem because we need to optimize with respect to a distribution, with respect to a function. Fortunately for us, it appears that it's not difficult at all. Why? Because we know that left-hand expression here does not depend on Q of z. This means that this sum does not depend on Q of z. And this means that if we try to maximize the first term, this is absolutely equivalent to minimization of the second term. And how to minimize the second term, we actually know, because this is Keil divergence. It's always non-negative, and we know when it's 0. It is 0 when and only then, when Q of z equals to P of z given x theta. So for each step, we have a just explicit equation. We know the optimal Q of z. So this is P of z given x theta 0. So this distribution depends on theta, and we compute it at the point theta 0. Each step is complete. Now we switch to M step, where we fix Q of z and try to optimize variation of our bound with respect to theta. So again, let us look at the variation of our bound. If we split this logarithm into two parts, we will know that the second part doesn't depend on theta at all. So the only thing that depends on theta is the nominator here. So this means that to maximize this lower bound, we need to maximize only the nominator. So this is a mathematical expectation with respect to this Q of z, which we already know from each step, of logarithm of complete likelihood. So we somehow managed to reduce the problem of maximizing incomplete likelihood to a sequence of problem for maximizing complete likelihoods. So by assumption, this problem can be solved quite efficiently. So in the case of the Gaussians, this corresponds to the case when all these are known, so we know which object was generated from which Gaussian. So when we found maximum theta star, we just take now as a new value of theta 0 equal to theta star, and repeat each step, and then M step, and again and again and again. What is good in this algorithm? The good thing is that our variation of our bound monotonically increases. So we can guarantee that somewhere it will converge to a stationary point of our logarithm of incomplete likelihood. So that's good, and in practice, in many cases, the algorithm really works. So what are another advantages? In many cases, E step and M step can be done super efficiently. So actually, in many cases, we just have explicit equations for this distribution and explicit equations for these argmax. But even if it is not so, many modifications of M algorithm are known, where we restrict the family of possible Q distributions, and we can always obtain convex optimization problems both on E step and M step, even in the case when explicit equations are not known. And one rule of thumb where EM algorithm, where EM framework, or where Latent variable modeling can be used is a case when we have to deal with extremely complicated probabilistic models which do not belong to so-called exponential class of distributions. Exponential class of distributions are the distributions that can always be represented as follows. So the rule of thumb is just to what? Okay. The rule of thumb is just to establish additional latent variables until this joint distribution belongs to the exponential class. And when it belongs to exponential class, we may easily run EM algorithm, and we can guarantee that both E steps and M steps will be convex optimization problems that are more or less easy to solve. So now let us see how it works in Word2Vec, in particular in skip-gram model. So instead of trying to learn the vector representations for words, we're now trying to learn vector representation for word meanings. Just for simplicity, assume that we know how many meanings each word has. Then we encode the number of particular meaning by additional latent variable zi. And so now we try to learn this inner representation, not just for xi, but for xi and zi. So this means that we try to learn different representations for different meanings of the word xi. So actually the model is almost the same. So this is again a product with respect to the nodes in our Huffman tree. The only difference here is that inner representation depends not only on xi, but also on zi. So if we know both xi and zi, then we can compute this likelihood function easily. The problem is that we do not know zi's. So in our training set, we know xi. So we know just words, but we do not know what meanings a particular word occurrence has. So we can have, say, a sentence, our train arrived to Waterloo at 2 p.m., but we do not know whether this, what was the sense of this particular occurrence of word Waterloo. Whether it was battle, whether it was song, whether it was railway station. Oh, actually, we know, but computer does not know, because this information isn't contained in our training set. So what do we do next? We have established this likelihood function. So the distribution of y given x and z. To complete the model, we need also to establish the prior distribution on z given x, and well, without loss of generality, and again for simplicity, let us assume it to be uniform distribution. So if word xi has k of xi different meanings, then we'll establish this prior distribution just by 1 divided by k of xi. So now we have a complete probabilistic model, so joint distribution on yi zi given xi, and we may run EM algorithm in order to learn inner representation for each meaning of each word, and outer representation for the nodes in our Huffman tree. So how it works? On each step, we need to estimate the probability of each particular meaning for the word xi if we know that its neighbor was word yi. So this is done quite explicitly. So this is just this equation. So in nominator, there's a likelihood function, the probability of observing yi, given that xi had a sense number, had a meaning number k, times the prior distribution that the word xi had a meaning k, and in the denominator there's just normalization constant. So this is summation with respect to all possible meanings of the word xi. So actually there's a misprint here. So this xi should be with a k. So this is summation from 1 to k of xi. So, but again, since the number of meanings, yep.
I have a question.
Sure.
What is the zi? It's a vector?
No, this is just a discrete number, the indicator. Yes, yes. So if, for example, the word Waterloo had 3 meanings, so the corresponding zi can be either 1 or 2 or 3. Correspond to a particular meaning of a particular word occurrence of zi. So here's actually the illustration. If we have such sentence, what we would like to expect at each step is the following probabilistic distribution. Well, I have named the meanings, but computer, of course, doesn't know that the first meaning means station, the second meaning means battle, the third meaning means song. Computer just knows that there's first meaning, second meaning, and third meaning. And in this context, we would like to expect that the meaning which corresponds to the station will have high probabilities, while the meanings which correspond to battle and so on would have significantly lower probabilities. This is what we want, actually.
But you know the 3 in advance.
Up to now, yes, just for simplicity, but then I will tell that it is not necessary. That actually we can adjust the number of meanings automatically. So since the number of meanings is usually quite limited, we can always compute this normalization constant, and this means that for each word we can easily compute this probability distribution. So then each step can be done, well, more or less efficiently. And on M step, what do we have? Actually, we take expectation with respect to log of complete likelihood, And we need now to maximize it with respect to inner and outer representations. So inner representations for the meanings, outer representations for the nodes in our Huffman tree. So again, M step is now almost equivalent to Mikolov's model, to standard skipgram. The only difference is that now we have a bit larger dictionary, because our dictionary consists not only of the words, but of the words and their meanings. So the question is, how do you think whether this scheme is efficient or not? Why not? Well, of course, if I ask this question, it's assumed that the answer is no. Well, we know that skipgram, it takes about less than an hour for a skipgram to train on the whole Wikipedia. So the question is how long this algorithm will work, approximately. Whether it will take hours or years.
It takes into account that Wikipedia has all of the disintegration separated.
No. And this is wrong, actually. Not for all words, just for some of them.
So it depends on how you define this Z. So how many Z you will have for every word?
Well, this is also true, but the main reason is following. EM algorithm is a iterative process. So just look at this scheme. On each step, we need to compute these probabilities for each word. And in Wikipedia, there's about 100 billion of words. So we need to perform full pass for our Wikipedia just to compute these probabilities. And after this, we use these probabilities to compute this expectation. And on M step, we need to retrain our skipgram with extended dictionary. And then we need, again, to perform the full pass on our training data set, and then completely retrain the model. So this is not efficient, because assume that EM algorithm will converge after 100 of iterations. So we'll need to take at least 200 passes through the whole Wikipedia, because we need to perform one full pass here and at least one full pass here. So this is not efficient. We have to make a lot of extra work, which is really not needed. So to overcome this difficulty, let us consider the concept of stochastic optimization. So please raise your hands, those of you who know what is stochastic optimization, what is stochastic gradient descent. No, absolute majority. Great. So what's the idea? I assume that we would like to optimize some function f of x, which consists, which is a sum of a large number of terms or functions fi of x. Say 1 billion of terms, so 1 billion of fi's. We would like to perform gradient ascent. So in order to compute gradient at a single point, we need to compute gradients for each fi and then sum them together. So seems not too efficient scheme, and the idea of stochastic optimization is just to take a mini batch of items, compute gradients with respect to them, thus obtain some value which is not full gradient, but which can be regarded as an unbiased estimate of the true gradient, and make one step towards this stochastic gradient, then compute stochastic gradient again using another mini batch, and so on. So Fermat's theorem by Robinson and Monroe says that if f of x is differentiable, and if we know g of x, which is a stochastic gradient estimate, which is unbiased, so its expectation equals the exact value of true gradient, then such procedure always converges to stationary point of f of x. So the problem is that the convergence is super slow. So it's sublinear, and in practice it means that it could take years to converge. This is why until the last decade, nobody actually used these stochastic optimization methods. But when mankind started solving big data problems, it appeared that this is the only technique which works on big data. So we have no choice but to use these stochastic optimization techniques. And this highly stimulated the research in this area. And Now it's known several modifications of stochastic gradient methods are known, such as SAC, SF4, IN2, ADAM, and some others, which sometimes guarantee linear or sometimes even superlinear convergence speed. And this is great, and it really works. So all theoretical guarantees are held in practice. So just for illustration, this is my favorite example. So what we did here, we took sum of million of parabolas, and these are level sets of the resulting function. Of course, we know that sum of parabolas is also a parabola, but computer doesn't know that. For computer, this is just a sum of 1 million of functions. And now we try to optimize it using stochastic optimization techniques. So it appears that to compute the value of this function at single point, it takes about 20 minutes. This is how standard stochastic gradient technique works. And here's the point where it converged after just 2 minutes. So we can say that we have captured the global extremum, but this point actually is pretty close, at least in terms of function value, to the global optimum. And it took us just 2 minutes, while to compute the function at a single point would require us 20 minutes. So these are some big data paradoxes, but well, it is really so. And here's an example how this SF4 method works. Again, it took us about 2 minutes, and we have converged almost to global optimum. Just for 2 minutes, while to compute the exact value of function would require 10 times more. So this is one of the reasons why stochastic optimization is so popular and why it really works when we deal with big data problems. So here's just a short summary of how stochastic gradients can be computed for several particular cases. So the first case, if function f is just a sum of a large number of items of fi's, so the simplest stochastic gradient would be we take just one component here and compute its gradient, and we can be sure that this is well, actually we should multiply it by n, of course, and after we multiply it by n, we can be sure that we have unbiased estimate of a true gradient. So now a bit more difficult situation. If f of x is just an expectation of some function h of x, y, and we compute expectation with respect to distribution over y's. Then how can we compute stochastic gradient? Well, we can sample from this distribution p of y, sample 1 or 0 points. So in this case, I sampled 1 point, y0, and then we compute gradient of h of x, y0 with respect to x. So this is again unbiased estimate for the true gradient, and this can be used as a stochastic gradient in the stochastic optimization techniques. And now the most complicated situation, which is, well, unfortunately, is met quite often in deep learning, in particular in deep neural Bayesian models, is this one. So this is again expectation of function of h of x, y, but now the distribution depends on x as well, and we need to differentiate it with respect to x. So now we cannot do like this because our distribution itself depends on x. So we sample from this distribution and we have to compute this value. The problem is that this value has extremely large variance, and so different variance reduction techniques are needed, such as controlled variates or recently proposed reparameterization trick. So probably I think that someone will give a lecture where he will describe what is reparameterization trick means, because this was really a breakthrough, which was achieved about 2 years ago, and which allowed to greatly reduce the variance of this stochastic gradient and opened new possibilities for training neural Bayesian models. But okay, never mind for now. So now let us return back to our completely inefficient EM algorithm. So there, on this step, we need to perform full pass with respect, through all of our training data and compute these distributions. And on M step, we need to completely retrain our skip-gram model with extended dictionary. So now the key idea. What if we, instead of completely retraining here, what if we just perform one step towards stochastic gradient of this value? Let us see what happens. So consider the gradient of a expectation of a complete log likelihood. So what is this? First, the complete likelihood on the training set is just sum of logarithms on well, separate objects. So it's sum with respect to I going from 1 to n, where n is 100 of billion equals to the length of our training set of these two terms. So this is likelihood, P of y given zi xi, and times prior distribution on the probability of a particular meaning for the word xi. So now what do we do next? We put expectation and differentiation inside of this sum using the property of linearity. So we know that both expectation and gradient are linear operations. So we can put them inside of summation and the gradient even inside of the expectation. So this is it. Note that here the expectation is taken only with respect to the I, because each item here depends only on one z. So ith item depends only on the I, it doesn't depend on the j's. Now we pay attention that actually the second term doesn't depend on the parameters with respect to which we are trying to optimize this quantity. So it doesn't depend on inner or outer representation. So its gradient vanishes. And so this is what we've obtained. So this is the true gradient for the quantity which we would like to maximize. And what would be its unbiased estimate? No, actually, this would be just one term here. So we can take arbitrary term here and compute its derivative. And this would be unbiased estimate. It would be stochastic gradient over our initial value. So this is it. We took just one object by random. And we will take this expectation. So this is just summation with respect to different probabilities of the i's of gradient of log of p of y, yy, given xi, and given the fact that word xi has a meaning number k. And this is the probability that the I equals to k, and we sum with respect to all, well, not j's, with respect to all k's, of course. So this expression we know from E-step, and what is especially good is the fact that actually to compute one stochastic gradient, we need to know only one distribution here, only for one I, only for one zi. So this means that on each step, we don't need to perform the full pass of the data. It's enough to compute this distribution only for one object, only for one I. And thus, we immediately obtain stochastic gradient for the M step. So instead of performing the full optimization on M step and the full pass on E step, we just compute one distribution on E step, and we take just one step towards stochastic gradient on M step. So this is actually the sketch of final algorithm. We start with building Huffman tree, just like we do in standard word-to-vec models. Then we fix an initial approximation for inner and outer representation. So these are parameters that we would like to tune. But in order to start the EM algorithm, we need to fix some initial approximation. And then we make just one pass of the data. And during this path, we go word by word. For each word, we compute this probability. So it can be done explicitly by a simple equation. And then we just make one step towards stochastic gradient with respect to our parameters theta, which consists of inner and outer representation. After we did one step here, we switch to another object, we compute its distribution, and then make one step here, and again and again. After one pass is finished, we're done. So actually, computationally, this is almost as efficient as a standard skip-gram model. The only difference is that here we need to, well, the space of inner representations is richer, because it doesn't correspond to words, it corresponds to meanings, and on average, each word has about 2 or 3 meanings. So the dictionary is on average 2 or 3 times more, and the procedure is 2 or 3 times slower. But again, it takes about a couple of hours to make one pass through the whole data, and actually that's all. after we performed one pass of the data, we managed to learn both inner and outer representations, and our algorithm is complete. But before I show some results of experiments, just several remarks of what was not covered in this talk. Of course, this was a bit simplified version of what is really working. So what are the differences? Well, first of all, here I did not use the fact that each word xi actually presents 2c times in our training table, and in these 2c times it should have the same meaning, because these 2c lines correspond to the same word occurrence. Here I did not use this fact, but it can be easily implemented in the model. The equations become just a little bit more complicated. Second, here we assume that we know how many meanings each particular word has. Of course, in practice, we do not know. And we would not like to know that. It would be good if we could define it automatically. Fortunately, we can do that using more sophisticated Bayesian techniques, which is known as a non-parametric Bayes. We establish special kind of prior on the i's, so p of the I given xi, using Chinese restaurant processes, and in this case, so this prior. So remember that in our model we used uniform distribution here. So if instead of uniform distribution we establish Chinese restaurant process here, we'll obtain another attractive property. Our model will be able to learn the number of meanings for a particular word. So some words will have a large number of meanings, some words will have a small number of meanings, some words will have just one meaning. So it will all be defined automatically using non-parametric Bayesian techniques, and this non-parametric Bayes slightly complicates our scalable EM algorithm. It becomes so-called stochastic variational inference, but again, the key idea is the same as I described in this large-scale EM. So now let us see how it works. So we run this model using making just one pass through English Wikipedia. And here are some examples. So we took word platform. For the word platform, 3 meanings, 3 different vector representations have been found. So in order to interpret these representations, what should we do? Well, for example, we could see at its nearest neighbors in the space of vector representations. So we take the first meaning of the word platform and look the closest vector representation for other words. So here they are, and from looking at them, we can conclude that this platform probably means something related to automobile industry. The second meaning definitely is related to railway, to railroads, while the third meaning definitely related with the software industry. Even more interesting, the word sound. So do you know that sound is not just an acoustic effect, but also proliv in Russian? And so here are exactly 2 meanings. The first meaning somehow related with something with water, while the second meaning definitely related with some acoustics. So this is, of course, just, yeah.
Could you tell again, please, how you go to the meanings you have Z for each word, and Z can be 1, 2, 3, or
Yep.
how you measure the distance between several words? Where is vector representation?
Well, first of all, Z is not associated with the word, it's associated with the word occurrence. So we can have, say, word platform 100 times in our training set, and there'll be different Z's. Because in this... Yep. And we managed to learn that platform should have 3 different vector representations, depending on its particular meaning, depending on its particular ZI, on its particular Z. So this is inner representation for the word platform when Z equals to 1. This is inner representation for the word platform when Z equals to 2, and this is when Z equals 3.
Obviously, there should be cases when there is not such discrete
difference between
we did not establish that in our model, so we assume that the meanings are more or less discrete. Oh, but this is just one minor step towards what you're talking about. Right. So this is just proof of concept. So it seems that it more or less works. And now let us see how it helps in word disambiguation. So we ran our model with alpha parameter equal to 0.10, 0.2. That's not quite essential, but I mentioned here just not to let you download the results of our model if you consider it necessary. So for the word Waterloo, so remember the example from which we started. Actually, our model found 5 meanings. Surprisingly, there was no meaning which corresponded to a song, probably because in Wikipedia, ABBA is not so popular, and there are quite few mentions of Waterloo as a song, which is bad, or at least for me, because ABBA is my favorite group. Anyway, what were these meanings? Well, let us see. So we take one sentence: who won the Battle of Waterloo? If we now compute the probabilities of different senses for this particular word occurrence Waterloo, we'll have this distribution. So we have, so we see that among these 5 senses, almost all probability mass is concentrated on the second meaning, whatever it means. And now let us see what are the closest words to this second meaning of Waterloo. Here we go. From the first side, it seems that it's all complete bullshit. From the second side, it seems that, well, not complete. Because here we have Austerlitz, we have Jena Auerstedt. So these are 2 famous battles where Napoleon, well, have achieved his famous victories. But what are the other words here? So, actually, the most of them were not familiar for me. I Googled them, and surprisingly, I discovered that all words here do correspond to battles. Well, this wasn't too surprising. This is what we would expect, that these words should be also battles. What's more interesting? All these battles were some crucial battles that defined the outcome of the war. What is even more interesting? In all these battles, either French or British or Prussian troops were involved. For example, this is Agincourt battle, the main battle in the 100 Years' War between France and Britain. So all other battles here were also battles where at least one of these 3 countries took part. And we know that in Waterloo, there were 3 sides. So there was a battle between French, British, and Prussian troops. The interesting thing here, top of Fushimi. So this is definitely not a battle in Europe. Actually, this was a main battle in Japanese Civil War. So how it's related to Waterloo? And the answer is that, surprisingly, or at least for me, was that in this Tomo Fushimi battle, one side was instructed by French officers, while another side was supported by British Navy. So actually, it still has something to do with the British and French. So now let us change the context. So this is completely different sentence. Our train has departed from Waterloo at 11 p.m. So here's the distribution of different meanings for this particular word occurrence of Waterloo. We see that the almost all probabilistic mass is concentrated around the first meaning. So now let us see what are the closest words to it. And bingo. Here we have top 5 closest words, different railway stations in London. So Paddington, Euston, Victoria, Liverpool, and Moorgate are all London railway stations. Well, the remaining words, again, are somehow related to railway to London. So this is it. Here are some useful links for those of you who are interested. So the first link is where code and documentation is available for our adagram. Just pay attention that it's implemented on Julia. I also uploaded 2 trained models with different values of alpha, just in case someone decides to download and to use in Q&A systems that you're supposed to develop during this hackathon. And finally, the paper with description of this model with the complete description, with all details, which was recently accepted to AI Stats. So it can be downloaded from archive. So probably this is it, the end of my talk. So just to conclude, of course, I do not expect that you understood all details, all equations here. It's not necessary. The presentation will be online, so you'll have a chance to go through the details if you consider it necessary. But what I would like to convince you in is the importance of this latent variable modeling. So using these latent variables, we're able to train from so-called weakly annotated training sets when not all information is present in the training set. And in this example, where we had a huge number of huge training corpus, but we did not know the particular meanings for particular word occurrences. So this is why this training set is weakly labeled. But even with this weakly labeling, we actually are able to train. These methods are especially effective when training sets are huge, of course. And using stochastic optimization, it appears to train them almost as fast as with a fully annotated training data set. So traditionally, latent variable models require much more time to train, but with the stochastic optimization and with this scalable version of AM algorithm, we can train them almost as fast as standard models. So this is it. Use deep learning and stay Bayesian. Thanks.
Question, please. So nobody has questions?
No, thanks a little bit. I have two questions.
Yep.
So the first question is, could you identify the three other meanings of Waterloo? And the second question is there any known benchmark to evaluate the performance of this system equation technique? Because there are other models as well.
Sure.
Developed on Waterloo.
Sure. Well, if our model works worse than other models, probably we would not be accepted to AI Stats. So all of the details about benchmark data are contained in our paper, so you can just go through it. And considering three remaining meanings, yep. So two meanings corresponded to two different towns in Canada, which are which have name Waterloo. And the fifth meaning, surprisingly, well, not surprisingly, corresponded to a famous BBC film about Battle of Waterloo. But it was separate meaning because although it was devoted to the Battle of Waterloo, the film became famous itself. So that's why particular meaning has been found.
I want to ask, is there maybe some way to use this kind of framework for structural relationship learning? Because it seems like there are a lot of implicit predicates that are embedded in this information, in these vectors. I mean that if we have some text with some basic maybe predicates that we have,
for example,
about objects. I mean, like Napoleon is person.
Okay.
Something else is. I mean, like Waterloo is battle, and then we want to have a relationship. General fought in battle X, and I mean that if we don't have some predicate, can we use this kind of framework to maybe suggest that there's exists a predicate that,
which relates to different concepts?
Yeah, that maybe involves several concepts in some maybe probabilistic relationship.
Seems that we can. I would even think that you would not need this multi-meaning extension for that.
I mean, like if you were familiar with the Never-Ending Learner project at Carnegie Mellon University that crawls the internet and reads a lot of text and tries to infer more probable
Mhm.
concepts between labels. It doesn't have this ambiguation, so it doesn't know about
Mhm.
things that have the same name. And it also doesn't know about transients of time. So all of the, for example, all the presidents are all presidents all the time forever. I mean, like, and the question is that it can take some words that it's like frequently occurred
Together.
together
Co-occurrence.
and try to infer like that it's a predicate that's separate from words but has a physical. So these words are manifestation of physical relationship. I mean, like, but it's not a discrete variable, probable variable that can be modeled by discrete probability variable. I mean, like, is there a way to find maybe if we have z, not a discrete variable, is there ways to find different data types embedded in data?
Well, I would say that the answer depends on how you establish your model with continuous z's, because I just don't know how to do that. I know how to do this with discrete values, and each discrete value corresponds to a meaning. But now you suggest to establish some continuous value for z, and this continuous value, should it correspond to a meaning again? But then how can we learn vector representation? Because vector is something discrete, right? We can, if we have 3 meanings, we can learn 3 different vectors. Now, when you have continuous space of meanings, how will we learn something? You see? But when you manage to answer this question, so probably after that, it will be possible to say whether it can be used or not for. This wasn't an answer, actually. Okay.
I'm sorry, it's from the trivial question, but you told that Robbins-Monroe procedure has a very slow convergence.
Mm-hmm.
And what happened with this stochastic approximation in high dimension case? So now it is fast?
I would not say it's fast. First of all, when we're dealing with these large-scale problems, we are not interested in finding accurate global optimum. We are okay if we find something more or less close to the optimal value. So this is why we just will stop this Robbins-Monroe procedure until it converges somewhere. You see? Well, this is one point, and another point is that now we know about that more efficient stochastic optimization techniques do exist, which will guarantee faster convergence. Of course, they have some restrictions, some limitations. There are cases when we can't use them, but if we can, we should use them.
Okay, so it's not just the same procedure.
Yes.
You're using new.
Yes. Yes.
And one more question. You know, of course, any encyclopedia is not a stochastic system. And everything which you are using here is just empirical work, nothing else.
That depends on what do you mean by empirical work. This is, of course, we do not claim that we have captured all possible meanings of words, for example.
But your procedure has no real grammars. All the stochastic inferences, you have no right to use them.
Well,
in a sense.
I see. The problem is that actually we have no choice. We don't have any more acceptable solutions. And when we have no choice, well, we have proverb in Russian. За неимением гербовой пишем на обычный. Well, this is the case. Yep.
I think that we should stop questions because we need to establish connection with Christopher Manning. So let's thank our.
Thank you.